Okay, time to start our next scintillating lecture. I assume that you find these just as interesting as I do. And today we're going to talk about generation of electricity. Now we're going to finish with a couple topics from before, but then we'll get to generation of electricity. This picture here, what is this a picture of? I swear I just had this biggest deja vu moment like I asked this before. And why did you say electric generator? Because that's what it says. It's also a picture of an electric motor. In my little deja vu moment, that was how you answered. I said the deja vu thing before I asked the second part because, I don't know. I didn't ask this before, did I? Yeah, I mean, no, on a previous day. Yeah, I referenced it, but we didn't actually have it on the screen last time. So electric generator and electric motor have the same design. We have the difference being that with an electric motor, which this is actually what the picture is designed for, we have the battery, and the battery creates a magnetic field in the loop, and then that field creates a torque to make the loop rotate. In the generator, we put something out here that makes it rotate. So we put work in to make it rotate, and then that generates electricity, which in this case would be charging the battery. So motors and generators are actually the same design, and that's something that we're going to learn about today. So start out with something I failed to define for you. The permeability of free space. All I said was that's a number that tells you how easy it is to magnify space. The value for the permeability of free space is an exact value. And just like all of our other constants, it's an exact value that goes on forever. Okay, not like all the others. The speed of light, at least it's only 8 digits. This is an exact value, but pi is an irrational number, so it has an infinite number of digits. But as long as you put 4 pi times 10 to the minus 7 in your calculator, you're fine. So that's the value for the permeability of free space. It tells you how easily you can magnetize free space. And the actual ampere, you might recall when we talked about charge, and I said the coulomb is not a base SI unit. Instead of the coulomb being the base unit, it is the ampere that's the base unit, and the coulomb is defined based on the amp. So how is an amp defined? If it's the base unit, it has to have a very reproducible way of defining it. And so the definition for the ampere is that if you have 2 wires separated by 1 meter, then the force acting on each wire is going to be 2 times 10 to the minus 7 newtons per meter. So you just adjust the current and measure the force until you get that, and then you have an ampere. Now let's go through this. First of all, this definition assumes infinite wires. Well, we don't have real infinite wires, right? But as long as they're really long compared to that 1 meter separation, we can treat them as infinite. Now this is kind of inconvenient because you would have to, for instance, if you're going to use this definition, you'd have to have wires that are like 100 meters long and then measure the force per unit length between them. Or you could, make a modification that's still going to give you the same meter. So let's look at how this works. So I have 2 wires, and I will draw straight lines for these wires because I can. So here's 1 wire, and here's a second wire. And they're separated by some distance that I'll just call D. And I want to find the force between these. Now to find the force, I have to have current because I make a magnetic field with current, and then there's a force between a current and a magnetic field. So the first question to ask is, should they be parallel currents or opposite, one up, one down? Which one do you want? This is just a question of your preference. One up, one down. One up, one down. So I'm going to make current 1 is going up, and current 2 is coming down. Both of them will have a magnitude of 1 ampere. How do I find the force between the wires? I specified I have a force, well, a wire with a current going through it creates what? A magnetic field. And then that magnetic field, having a current going through the magnetic field, creates a force. So I'm going to have two equations I'm going to have to utilize. I'm going to have B is equal to mu naught I over 2 pi r. That's the magnetic field produced by a wire with current I going through it at a distance of r away from it. And then, so that gives you the magnetic field. What gives me the force? It starts with I, then it has the L vector cross B. Okay, is that what you said? Okay, I just didn't hear it. All I heard was the I, and I was like, well, that's a start. Okay, so I'm going to have to combine these two equations. So first, the magnetic field. If I take wire 1 and I say, okay, wire 1's making a magnetic field, what direction is the magnetic field due to wire 1 at wire 2? It's going to be into the page because you take your thumb of your right hand, point it the direction of the current, and then your fingers wrap the direction of the magnetic field. So wire 1 will make a magnetic field that goes into my screen on this side. It would come out over here because it's going around in circles. So now I have the direction of the magnetic field. I know its strength is going to be mu naught I over 2 pi r. What was r?
The distance.
The distance from the wire to my magnetic field. So in my picture, what symbol do I use for that?
D.
D, right. Now I want to find my force. First, let's get the direction of the force. How do I find the direction of this force? The right-hand rule. And so this is IL cross B. Which I was in the magnetic field equation? I1 or I2? That was I1 technically. And which one is in the force equation? I2. And remember, the L is the direction of the current there. So I2 is going what direction? Down. Hence L is pointing down. So I take my right hand and orient so my index finger points down. Then keeping my index finger pointing down, I orient my hand so what points? What direction? Okay, the middle finger needs to point in the direction of the magnetic field. So in this case, I need my index finger down and my middle finger so it's going into the board. And so my thumb is pointing to your right, correct? My left, so I'm going with your right. Yes?
Where does it say that? Oh, are you just looking at the magnetic field?
I'm just looking at the picture there, yes.
With the axis
Yes.
going inward?
That's right. Okay, so we have meh, meh. And so is this an attractive or a repulsive force? What did you find for the direction?
It's to the right.
It's to the right, so is that attractive or repulsive?
To what?
To the... Is one wire attracted or repelled by the other wire?
It's repulsive.
Okay, it's repulsive, being pushed apart. Now, all of our angles are 90 degrees, so that means the magnitude of the force is just I2 LB, I2, which is then going to be I2L, and for B I put in mu naught I1 over 2 pi, and the separation was D. If you simplify that, you get force is equal to mu naught I1, I2, L over 2 pi times the separation. So there we found the equation for force, and if you're paying attention, there should be something troubling to this. What's troubling? The force depends on what variables? Okay, that's the troubling one. The troubling one is the force depends on the length of the wire. But I started off by saying, well, we have to have an infinite wire. And so that means infinite force, right? That's why we just take this and say, divide both sides by L, so that we have the force per unit length is mu naught over 2 pi I1, I2 over D. And now we can see how it works out if our distance is 1 meter and we define I as 1 amp. What force will it give us per meter? 4 pi times 10 to the minus 7. What were the units of mu naught? Newtons per ampere squared. So putting in the definition of what the force per length should be if it's 1 amp, 4 pi divided by 2 pi is 2. Everything else was a 1, so we end up with 2 times 10 to the minus 7. Newtons don't cancel, the amps canceled, and meter was a new one. And so that's the way the ampere is actually defined, is the current that's going to make the force per meter 2 times 10 to the minus 7 newtons per meter. Yeah?
On the magnetic field of that wire, how did you decide that it was I1 and not I2?
Because I was looking at the force on I2, then the magnetic field was the magnetic field created by I1. And I could have gone the other way. I could have said, okay, so what's the magnetic field at I1 caused by I2? Then using my right-hand rule, I would have had, that current's going down. I forgot we had opposite directions. So since that current is going down, my fingers would wrap, and that would be going in, and I would end up with the force going like that.
Isn't the current going up?
This current is going up, but this is the magnetic field created by that current, by this current. Right. The magnetic field that I drew here was created by this current.
And so the force over L, that's just what was that to?
That was the force per length acting right here. But of course, by symmetry, it's also the force per length acting here. Right? Because you can see the equation is completely symmetric between the two wires. So if the currents are opposite directions, are the wires attractive or repulsive? Repulsive. If the currents are the same direction, what does that predict then? They're going to be attractive. Okay, a homework question. I was actually going to do this in class before, but we didn't do it. We have a wire that's assumed to be very long. And then we have down below, I'm going to sit down, I'm tired. Down below, we have a loop with current in it. And the question is, what's the force on the loop? What is your method going to be?
Do it like the side or side.
Okay, step 1 is break it up into each of the sides and do each side separately. Part 2 then, how did I start the last problem? Define the force between wires. What did I do? I found the magnetic field. I don't even know who said that, but I heard magnetic. So I found the magnetic field. Now a question you have to ask yourself is, do I find the magnetic field created by this loop at the wire, or the magnetic field created by the wire at each side of the loop?
The wire at each side of the loop gets us on the loop.
Okay. Now, it would have worked the other way. Because it's on the loop is not the perfect reasoning. But it has to be that way because we have to have a very long wire to actually calculate the magnetic field created by a piece of wire. If you were in the other physics class, yes, you could use the Biot-Savart law to find what the magnetic field at the wire will be due to the loop. But you know what? Only 7 of you are in the calculus-based class. So for everyone else, you can't do it that way. You have to find the magnetic field created by the very long wire. So first let's do directions. What direction will the magnetic field be down here due to the current up above? Define what you mean by down. Because I wouldn't have said down.
What direction of the field into the page?
Okay, there we go. The field will be into the page because you make your thumb point the direction of the current. Down below, it's going into, in this case, the screen. And so that defines the direction. So my magnetic field down below is going to be, change back to the pin, change to a black pin. That's enough. Magnetic field is into the board or into the screen.
How did you figure out it was going in?
Okay, because I took my right hand and put my thumb parallel to I1. And then I wrap my fingers to below I1 because my entire loop is below, and they go into the screen at a position below the I1.
Because you're looking at the force that the I1 current is doing on the second.
Well, I'm finding first the magnetic field created by I1. And then once I find that field, then I find the force.
Okay.
So the first step is I find my magnetic field is pointing into the screen and has a magnitude of, that's not a B, and the R is going to vary. It'll be 7.5 centimeters for the top wire, 30 centimeters for the bottom wire, and it will, whoa, not 30, 17.5 for the bottom wire, and it will vary between those for the side wires. Okay, so there's my first step. What's my next step? Okay, I'm going to write down the equation first. Force is equal to I L vector cross B vector. So now I'm going to look at the directions, as she said, for each of my four forces. So what direction will the force be on the upper wire?
So that equation, just to clarify, that is saying the force of the magnetic field is equal to, is that what you're saying?
This here is the force created on the wire by the magnetic field. So what direction is the force on the top wire here? The top wire in the loop?
Down.
Down. So I'll call that Ft for the force of the top wire. Let's go to the bottom wire. What direction will it be? Up. If you got the top one is down, which you got by taking the magnetic field, well, first put your fingers in the direction of the current. Second, in the direction of the magnetic field. Your thumb points down. So that's how you got the one for the top. For the bottom, the current just flipped directions, so that means the force is going to flip directions. What about the sides? Let's take this side here, your left side. Current is going down. What direction is that point? The force left is pointing into the right. And what direction would the force on the right side be pointing then? Now, we're going to apply a little bit of logic. If I take the upper wire and compare it to the lower wire, how are the magnitudes of those forces going to compare?
The bottom one should be less.
The bottom one should be less. Why?
Greater separation.
Greater separation. The magnetic field will be weaker farther away, and so the force in the bottom one is going to be smaller than the force on top. We're going to have a net downward force from those two. What about the force on the left compared to the force on the right? They're going to be the same. So what are those two going to add up to? Equal. That's very good, because without calculus, you would be done for the left and right side. You can't do those without calculus. But just applying logic, we know that they're going to add up to 0. And so we end up with our not so difficult relationship that force left plus force right equals 0. And so I just need to find the force top and the force bottom, and then I can add those and I'll be done. So the force top would be equal to I2, since I2 is the current going through the loop, multiplied by the length of the top, which I'll just call L as 30 centimeters, times the magnetic field, which is mu naught I1 over 2 pi, and this distance here I'll call D1. So that's the magnitude of the force on the top. Its direction is down. What about the magnitude for the force on the bottom?
I2, and then we need L plus times that force.
The L was just the length of the wire.
Oh, sorry about that. Yeah, L. And then times mu naught I2 pi, and then the D will be the A plus times that force.
And so I'll just call this D2, where D2 is the distance down there. So D2 is equal to 17.50 centimeters. D1 is 7.50. Now, I'm not going to put numbers in. We don't have enough time, but you can see the method. Now that we have that, we'll find force top is bigger than force bottom, so the net force is going to be a downward force, and we'll get the numbers from this. Do remember, when you add the vectors, there was somebody who forgot and did this wrong on the test. If you add vectors and one goes like this and one goes like this, you don't just add the magnitudes. You have to take the magnitude in one direction minus the magnitude of the other one, because they're opposite directions. Right? There's one of the problems. The answer was 350 something or others, because you had 450 plus 100, but the 100 was opposite direction, so it was 350. Any questions on that problem? You all understand the right-hand rule applications? Chad.
So when you talk about the force on the left and the right sides,
Yes.
0.
The sum of the two is 0.
Right. If we're talking about a real-world application of that, though, would we see those sides flex?
In real life, depending on the rigidity, yeah.
It's not a force that's acting across and canceling. It's a force.
Well, we're treating this as a rigid loop, right? If it's not a rigid loop, then they're going to go like this. But then if you still look at the total force, if the sag is the same on both sides, it'll still add up to 0. Question, Diksha?
So if the force on the left and the right is 0, then why is the sum of the forces on the top and the bottom?
Okay, the left and the right, for a little piece right here and a little piece right here, the magnetic fields at those two locations, those are supposed to be the same distance from wire 1. So the magnetic fields are the same at those two locations, and the forces are in opposite directions. The current's the same. So they have the same magnitude in opposite directions, so those add to 0. And then for every spot on the left one, there's a corresponding one on the right where I can make that argument. So even though the force here is smaller than the force on this little piece here, there's always going to be a little piece on the other side that adds them together to 0. Right, in a calculus class, you would actually add up all of those little pieces to find the total. But that's not what we're doing. Okay, next question, and I actually am low on time, but this is so useful to know. Chad, I think it was, asked me after our class on Tuesday about household wiring and magnetic fields. In your household wiring, you have two wires that are running parallel to each other, but the currents are going opposite directions. So that's like what we did for our first problem, where we found the force between two long wires. Is the force between those wires going to pull them together or push them apart? It's going to push them apart because they're opposite directions. But a key here is you have 60 hertz AC. You have electricity that's going back and forth in those wires at 60 times per second. And so having current in a wire creates a magnetic field. And because you have those wires separated by a distance, you're going to create a magnetic field that's fluctuating with those wires. If you have another wire next to it, that fluctuating magnetic field can cause charge to move in the second wire. And so you can have interference between wires. So what we want to do here is to find out just how strong the magnetic field is as we move away from a wire. So here we have two wires separated by a distance d, and we're going perpendicular to that, a distance r away, and saying, what's the magnetic field? Now, first things first. What direction is the magnetic field created by the top wire at point P? Up and a little to the right, because we're not straight out horizontal. So there's the magnetic field from the top. Now what about from the bottom wire? It's going to be down and to the right. So we just use the right-hand rule to get those two directions. How about the magnitudes? What's the magnitude of the magnetic field created by current in a wire? Okay. Mu naught I over 2 pi times the radius. Well, the radius is not this r. The radius is going to be the distance. Oh, that was beautiful. The radius is that distance. So how do I calculate that distance? I'm going to put d squared divided by 4. That is the square of d over 2. So that's the magnetic field strength. It would be nice if I was done, but I'm not. How do the magnetic fields add? As vectors. So I need to break these into components. So if I break these into components, this angle here is the same as this angle here. And so if this side here is BB, what is the opposite side going to be? If the hypotenuse is BB, what's the opposite side? Yeah, it'd be BB sine of theta. How do I find sine of theta? Well, I have a triangle here. Sine theta is opposite over hypotenuse. So sine theta has to be the opposite side, which was d over 2, divided by the hypotenuse, which is square root of r squared plus, well, right in the same way as I did before. So there's my sine theta. Sum of the forces in the, let's define an xy component system. Sum of the forces in the x direction is equal to, what would you tell me about the two vectors when I add them together? How do the x components compare? How do the y's compare? Okay, the x's are equal magnitude and direction, so it's just going to be 2b bottom sine theta, or 2 times mu naught I over 2 pi so there's the B and then sine theta. So that's the force in the x direction. And then what about in the y direction?
Just add to 0.
We have one up, one down, equal and opposite, so they add up to 0. So I didn't even worry about finding what cosine theta is because I know it's going to be the same, just one up and one down. So our answer, whoops, I put F instead of B again. These are all just B's, magnetic fields. Our answer is the sum of the magnetic fields in the x direction is equal to B total is equal to, notice this 2 and that 2 will just cancel. And since I have these two square roots multiplied together, so there's my magnetic field. Now what if R is a lot bigger than D? My people in Physics 252, we essentially did this problem. What do you do if R is a lot bigger than D?
In the sense they say that's approximately the same as it's a speed over 2 pi r squared.
So that R just becomes what R was originally. And my magnetic field total simplifies to mu naught I d over 2 pi r squared. So now we're able to calculate how big the magnetic field is for a given current, and then it gives us representative numbers. Says if D is equal to 5 millimeters and R is 1 meter and current is 5 amps, what's the magnetic field? Yeah. So if I put in those values, I'm actually going to do this because it's important to do the last part, the comparison to the Earth's magnetic field. No, it's 5 millimeters. It's 5 times 10 to the minus 3 meters. So that leaves me a 2. 2 times 5 is 10. Times 5 is 50. Ten to the minus 7. 10 to the minus 3 is 10 to the minus 10. And that would be units of so the B total would be 50 times 10 to the minus 10 newtons per ampere meter, or 5 times 10 to the minus 9 newtons per ampere meter, assuming I didn't make any mistakes here in my calculation. How does that compare to the magnetic field of the Earth? It's 1/10,000th. So it's a very small magnetic field compared to the magnetic field of the Earth. That means you're probably not going to get a lot of interference with wires if you're separated by a meter. But if you bring those wires so they're separated by just a few centimeters, you will start to get significant magnetic fields. You'll multiply it. If you brought it down to 1 centimeter, that would make it so it's about the same as the Earth's magnetic field, but it's fluctuating back and forth. And that will cause interference. So as I said to Chad when he asked about this, if you're doing household wiring and you're putting in your data communications, your internet cable, you want to make sure that that cable, when it has to cross the power lines, is perpendicular so that it doesn't cause as much interference. If it's parallel, you're going to cause a lot more interference with the magnetic fields. Okay, now this slide you might recognize is the last one we had last class period. It won't be the last one today. Talking about solenoids and showing how a solenoid is constructed. I know one group made one yesterday, right? Right. And a usefulness here in the magnetic MRI. MRIs, back when I was a child, they were introduced and they were called nuclear magnetic resonance. And people got really, really scared. Nuclear! What are we going to do? Nuclear! They just did not realize that their body's made up of atoms and each atom has a nucleus. And this is looking at the nuclei. It's not doing anything that has to do with, damaging, radiation or anything. But they just changed it. They dropped off the N and now just call it MRI, magnetic resonance imaging. Yeah.
Is it specifically proton NMR, or is it just?
Well, I think it is because that's your homework. They're very specific for what they do for the medical MRI, right? If you're doing it for organic chemistry, you're a lot more broad in what you're looking at than what they do in the medical application. So, our first clicker question about a solenoid. Do you see a nice exploitable symmetry that we could use Ampere's law on? And are you just answering randomly now, Jaron? Okay. We had 12 people that said yes, cylindrical. 1 that said yes, planar. 5 that said yes, something else. And nobody said no. I would have expected, what would I have expected? 7 people to say this answer. Because it's the correct answer and it's what we did in class yesterday with 7 people. This doesn't have a nice simple symmetry. You can't make a circle or something like that and use Ampere's law conveniently. But what is the shape we use? One of you people that's in the Physics 252 class? A rectangular loop. So you make a loop that goes something like this. And as long as you're close to the center of a solenoid that's fairly long compared to its radius, then you're going to have a uniform magnetic field in the inside, and the magnetic field is going to be perpendicular to the sides. Now I know in this picture it's not perpendicular sides. The reason is because my solenoid's not very big. But if you have a big enough solenoid, then it's going to be perpendicular on the sides. Why is that important? Because Ampere's law was that circulation thing, which is the sum, for non-calculus, that's the sum on a loop of B dot delta L, the length of each side, is equal to mu naught times the I enclosed. What does a dot product mean? Only the parallel parts. On this loop in the center part, the magnetic field is parallel to that wire. So on the center part, I have the magnetic field in the center multiplied by whatever length. I'll just call that A. That's what I get for B times the parallel length for the center part. Going up the side, how much of the magnetic field is parallel to the side? None of it. It's perpendicular. So since B is perpendicular to L on the side, I'm going to have plus 0 because B side is perpendicular to delta L for the side. And then I get up to the top. And this is where it gets a little tricky. We actually take this thing and we say, let it go up infinitely long. What's going to happen to the strength of the magnetic field if you get infinitely far away from the coil? It goes to 0. So then we're going to have plus 0 because V top is equal to 0. And then we come back down the side. We add those together, and that gives us our total circulation. That gives us the left side. So we have sum of B dot delta L on the loop is equal to B center times A. But Ampere's law tells us that that's equal to mu 0 times the charge enclosed, or the current enclosed. Now the current enclosed is actually the trickier part of this, because I have multiple wires enclosed. The number of wires enclosed is going to depend on how big I made that A. And so what we do is we just use the total number of loops divided by the total length of my coil. I didn't mean to do that. I was not thinking clearly. We will define as lowercase n. So n is the number of turns per unit length. The number of turns within my loop is going to be the width of my loop multiplied by the number of turns per unit length. Right, turns per length times length, turns. And so the current enclosed is going to be the current in the wire I multiplied by the number of turns. So I have that equation, which simplifies to the magnetic field in the center is equal to mu 0 I times the number of turns per unit length. It works out actually pretty simple to do that. Yeah, question?
How many turns are in there?
In this one here, it was not specified.
Okay.
On the next page, it will be specified.
Okay, so tell us.
How do you get the direction of that magnetic field? The right hand rule. Wrap your fingers in the direction the current is going around the coils. Your thumb points the direction of the magnetic field in the center. What about the magnetic field outside? Well, I know the magnetic field outside is going the opposite direction, and it's much weaker, the end. Right? We don't attach a number to that. We just go on. So, sample problem from the homework. This is actually homework due today. It was asked, I believe it was due today. A student asked about it yesterday, and at first I was like, well, look it up. And I was like, oh, wait a minute. No. They gave us the information. What we have here are two different problems, two completely separate problems, if you will. One is an MRI, which has 400 loops per meter. That is, N is equal to 400. It said loops, I said turns. I'll put what it said. And it has a coil of radius equal to 0.660 meters. And the magnetic field is equal to 1.20 Teslas. And then it asks us to find, doesn't it say to find the current? Yeah, calculate the current. To answer this, I say, okay, this is a coil or a solenoid. And what's the equation that finds the magnetic field for a solenoid? That's for a wire. Okay, so it's the one I just did, the mu naught I times N. Well, I'm trying to find I, so I is just equal to B over mu naught N. So that's 1.20 Teslas divided by 4 pi times 10 to the minus 7 newtons per ampere squared. And then the number of turns 400 per meter. Notice I didn't even put the loops here because loops are not technically a unit. It's just a number of them. So putting this together, what do you get for the answer? 2,300 some?
2,387.
Okay, so I'm going to write down. That's a really big current. Now, she did the calculation, I didn't. She's probably pretty good, but you should do your own calculation. Don't trust somebody else to do your calculation. That'd be a huge current, right? Even with wires with really low resistance, that's going to be a huge amount of energy that is lost to I squared R, the power used by the resistors. Right, I squared R, you square that and you're into the millions. If the resistance is just like 1 ohm for the entire length, you still lost a couple million watts. So you can see superconductors would be really good for this in terms of the energy loss. Then it asks, what is the field at the center of a proton? Now this is the question that I was asked, and at first I said, well, look it up. But then I read the top part of the problem where it says, the magnetic field of a proton is approximately like that of a circular loop. That's what you're supposed to do. So we have a circular loop with radius equals 0.650 times 10 to the minus 15 meters, and current equal to 1.05 times 10 to the 4th amps. And so for this, it's not a solenoid. It said it's like a circular current loop. The equation for the magnetic field created by a loop was different. For a loop, the magnetic field in the center is mu naught I over 2R. It's different because you just have one loop and it's not spread out like a solenoid. And so I'm not going to do the numbers on this one, but that's how you're supposed to find what the magnetic field at the proton is doing that calculation. It does not like, I did it on mine and it did like my answer. All right, so I want to make sure we have that covered. We have 3 minutes to cover the new material. Excellent. We obviously aren't going to get what I want to do. Motional. Notice there's no emo here. We are not emotional EMF. It's motional. The EMF produced by something moving. If I have a metal rod that's moving in a magnetic field, we have learned that the charges, the individual electrons in the metal rod, are going to feel a force because they're moving in the presence of a magnetic field, provided they're moving perpendicular to the magnetic field or have a component perpendicular. So if I have a rod that goes through a magnetic field, there's going to be a force on the charge. Now, how do we find the direction of this force? Right-hand rule. The equation for that force is force equals QV cross B. So I would take my right hand and say, okay, the first thing in the cross product is V. So I'll take my index finger and point it in the direction of V. The second thing in the cross product is magnetic field, B. So I orient my hand so my middle finger points in the direction of the magnetic field, and my thumb points up. Why does the arrow point down? Because they're electrons. The Q is negative. So it's a negative upward force, which means a downward force. Because they're electrons that can move. So as the electrons move down, we're going to develop a negative charge down here. But where do those electrons come from? Yeah, so we're going to develop a positive charge up here. So now we're going to form an electric field. And the electric field will be such that we balance, okay, this picture doesn't even help me. The electric field will be such that we balance the upward force due to electric field with the downward force due to the magnetic field. So the upward force is QE, the downward force, what we just did, minus QV cross B. And it turns that the electric field is going to be minus V cross B. So I have this object going through a magnetic field, and it creates an electric field that depends on the strength of the magnetic field and the speed. Question?
Is that the speed of the surfaces moving through the thing, or is it the speed
That's the
of
speed of the
actual-
rod moving.
Okay.
But we also learned that if we have a uniform electric field, that V equals Ed, that is, the voltage difference is equal to the electric field times the distance. In this case, use L for the length of the rod. And so taking into account you might not be going parallel to the magnetic field, theta is parallel. Might not be going perpendicular to the magnetic field. So theta is the angle between the velocity and the magnetic field. And it turns out the voltage you create is the speed multiplied by the magnetic field multiplied by the length, and then sine of the angle between the magnetic field and the velocity. For this reason, an airplane traveling through the air, we have the Earth's magnetic field of about 5 times 10 to the minus, what? 5 times 10 to the minus 5 Teslas. And you have a wingspan that's somewhere on the order of, let's say, 50 meters. If they're going at a reasonable speed, they're going to develop a reasonable voltage difference across the wings. You could actually power your iPhone just by, putting a rod across and using that to power it. So this is how we get motional EMF. We develop a voltage by having something moving through a magnetic field. And unfortunately, Faraday's law will be covered on Friday.
What concept coaches do you need on Friday night?